Today, I would like to talk about an interesting little piece of astronomy news. Plot thickens in the hunt for a ninth planet. At first, I kind of figured this article was going to be very, pop-sci. And I don't necessarily mean that in a negative way, but I figured this article was going to be very, loosey-goosey in a way and not super scientific and just be like, hey, there's some weird stuff happening. But I should have known better because, this particular website, the physics.org website, would not be posting something like this if it didn't have a paper attached to it. And what I found was that there's actually kind of a really interesting sort of story behind this and an interesting look into a particular theoretical mindset that I don't necessarily agree with. I talk so much about dark matter, it's only fair for me to talk about the other side of the coin. Let's talk about Planet 9 because, people hear about it and it's always a question that comes up to me. Oh, what do you think about Planet 9? Oh, do you think there's actually a ninth planet beyond Neptune? And my answer was always no, I really don't think so, but I didn't really know the evidence super well. I figured if it was there, we would have found it, was mostly my thing. This is one of the best papers that I could find regarding Planet 9. It is, I believe, a review article published back in 2019, and it is a long boy. It goes on and on and on and on and on, and I'm not going to lie to you, I did not read the whole thing. There's no way in hell I could have read this entire thing. Look at it. It's big. This is a big boy. But I did look at some of the more interesting things in it, and I'd like to distill them here for you. The first thing that sort of clued people off that there might be a ninth planet was looking at some things called Kuiper Belt objects. Kuiper Belt objects are objects in what is called the Kuiper Belts. This is a collection of rocks, effectively, far outside the orbit of the known planets. Here are the planets, here's the inner solar system and the asteroid belt. The Kuiper Belt objects are all of these blue points on the outside. They're very, very far out. So we're talking about objects beyond Neptune. It's effectively a secondary asteroid belt, except it's way further out, and there's also another bigger one outside of that called the Oort cloud. We're not going to talk about this so much today. We had a selection of a few of these objects that we've been tracking. We found that a lot of them fit into three different categories. Either stable, which means that their orbits did not seem to be changing, they were pretty stationary. Some that were metastable, which were kind of right on the razor's edge between being a stable orbit and a not stable orbit. And those are what we call unstable, which change very quickly in terms of solar system time. Your time is in giga-years down here on the bottom, which means we're talking in terms of billions of years, actually. Some of these objects do what we are expecting to do. Others are perturbed by something. Now, this something is a question mark. Some of these objects are perturbed by Neptune, of course, because Neptune is out there right on the edge of the Kuiper Belt, as we saw in this little illustration right here. But some of them are being perturbed by something else unexplainable by Neptune. In this particular diagram, they point out 6 of these purple ellipses. These are the actual orbits in physical space, and this is to scale, of 6 objects that we have located that we know are not directly coupled to the action of Neptune's gravity. But they still display some level of unstableness to their orbit. One of the answers to that is that there is a ninth planet, a large planet, multiple Earth-scale planet, that is somewhere in the Kuiper Belt that is slightly tugging on these things every time they pass near it. The reason that people suspected it was a planet, or one of the reasons they did, is they ran simulations. So this type of physics and math can be done analytically, and it was, and they found the equations all worked out to give us results like we're seeing here and here. But they also decided to throw it into a computer simulation, and when they did that, they found that the data also matched up with those computer simulations. So what these computer simulations are showing is they're showing us what's called a phase diagram, a phase space diagram. I'm going to be focusing on the panels on the left, but the same principles I'm about to explain over here can apply to the right. We're just talking about different physical things. So over here on the left, what we're looking at is a polar phase space diagram. What that effectively means is we're talking polar coordinates, so we're talking about angles from one of these two axes, and we're also talking about the radius, right? So our coordinates would be read as a radius outwards and a direction in terms of angles. 130 degrees would be a possible data point on here. Now, of course, what do each of those mean? In a normal Cartesian plot, we're talking like distance versus time, or force over distance, right? Something like that. In this case, what we're talking about here is eccentricity on the radial axis, and effectively direction from the sun on the polar axis. At the very center, we're looking at a circular orbit, and as we move outwards radially, we're getting more and more eccentric, which is why all of these objects are on the outside of this circle, because they're all very eccentric orbits, some more than others. And then the polar direction, the actual angle we're talking about, that is the angle at the furthest point from the sun relative to planet 9. Effectively, what we're saying is, if we take a look at all of the orbits that could be formed as a result of just throwing a bunch of Kuiper Belt objects at an orbital distance close to this supposed planet 9, what kind of orbits would we get? What would their eccentricities look like? And where would they end up in relation to planet 9 itself? And when we do that, we get all of these points. The blue points here are high densities of objects in our simulation. And we can see that the high object densities in our simulations over here on the left on both of these plots line up very well with a lot of the dots that we're seeing in our data set. So in other words, when we run a simulation, we find that a lot of the objects that start to actually form as a result of the dynamics present due to a ninth planet end up in this phase space over here with high eccentricity and in this little spread of angles. And our data set shows us a bunch of points that are very high eccentricity that lie in about that range. Of course, we have some other ones over here that don't, but that's okay. Our simulations with the planet 9 are consistent with our observations of the current solar system. Now, mind you, that does not mean, it is not definitive proof that there is a ninth planet. This is a correlation and causation thing. It may be possible that these two data sets are correlated. They could have this same effect due to two different things. Us plopping a planet 9 down there isn't the only possible way we could get a plot that looks like this. It just so happens that if we do plop a ninth planet in there, we get a plot that looks like the data. They are not necessarily causally linked. Very, very important. The same thing is also true on this right-hand pane, though I'm not really going to go over what this one is explaining. I'm mostly just going to point out that this yellow circle is what we call the RMS value of these data. Effectively, it's telling us where most of the simulated particles that we put in ended up within, and most of our data lies in or close to that circle. Another good indicator that this could possibly be a ninth planet. So that's more or less what this entire paper does. It explains that, it goes on and talks about some of the actual possible sizes of this planet. It runs a whole bunch more simulations. That's only one of a few they ran with different parameters. All of them line up pretty well. And long story short, there's a very good possibility based on these data that a ninth planet could explain these phenomena. Now, mind you, this does not mean there is a ninth planet. This means that a ninth planet could explain what this is showing. Not necessarily causality, definitely correlation. Now, what the actual paper that I wanted to talk to you about today is saying is that we don't need a ninth planet. Instead, we have this concept called modified Newtonian dynamics. I talked about modified Newtonian dynamics a few times when I talked about dark matter. They're kind of the two competing solutions to the problem of the missing mass issue. And I've talked at length of this, so I won't bore anybody anymore with it. But long story short, if you look at a galaxy and you look at something like the rotation curve of the galaxy, we are missing a significant amount of mass. We can also see this in terms of the fact that galaxies are held together by seemingly not enough mass. They should rip themselves apart due to their rotation, but somehow they're keeping themselves together. There's some sort of cosmic glue. And dark matter posits that it's some sort of physical matter, gravitational matter that we cannot see and doesn't interact with light. That's the dark matter hypothesis. And it's the one that's gaining the most traction. It's the one that most scientists will agree on makes the most sense at the moment based on our observations. However, there are some people that posit that modified Newtonian dynamics, or MOND, M-O-N-D, is the real reason that this is occurring. And the difference is that modified Newtonian dynamics posits that there isn't extra mass, but the mass affects the gravitational field differently at large scales. It's complicated, and I'll do my best to explain it, because they give a good introduction here. This is actually a pretty reasonable introduction. If anybody's watching this back, pause the video and take a read through all of this. There's actually a pretty good introduction here, and same with this section down here on the galactic field and the phantom mass. But I think I can do it faster. What MOND suggests is that the gravitational field is not just the normal Newtonian gravity, which is this part right here, but we also have this other factor here, phantom mass. Effectively, it's saying we have the part that's from the gravitational field of the galaxy and the solar system, and also this extra term over here. This stuff is very willy-nilly. Effectively, it's just saying there is something that affects gravity at distances far enough away that it would be small enough. If we had, say, the solar system, things close to the sun would be affected by normal Newtonian gravity, which explains why all the planets act the way they do, and if you get really close, then you get into general relativity. MOND postulates that not only do you have that, you also have this extra bit on the right-hand side of equation 2. I really wish I could, highlight this better. I can draw on it, can't I? This part right here. And this part right here suggests if we get to a point where Newtonian gravity is weak enough another type of gravity takes over. Up here, we can see the actual physical interpretation of this. This scale, this color scale right here, this color gradient, is effectively showing us what you can consider a phantom mass. Effectively, it's where would we need to add mass such that Newtonian gravity would work as written. Now, mind you, this is not positing any actual dark matter or any actual real physical matter in that space. It is instead saying the gravitational field acts as if there was more mass there compared to Newtonian gravity. It's not real mass. We're saying gravity acts as if there was more mass there, but there isn't. In this particular diagram, the sun is right here at the center, which we would expect to have zero phantom mass, which is what we look at, because as you're close to the sun, we wouldn't have any effects from this MOND at all. And in this direction, towards the positive z-axis, is the galactic center. So what we're seeing is that if we take MOND into account, we see this extra sort of halo of phantom mass, and we also get this little node up here of phantom gravity towards the direction of the center of the galaxy. If you do all of this, and you take all of that into account, it predicts that we would end up having all of our orbits of objects sort of tend towards the center of the galaxy as they leave the center of the solar system. So as things get further away from the sun, we would get an extra pull towards the center of the galaxy because, well, there's extra mass in that direction. Again, it's not really mass, but we would get an extra pull in that direction, which would effectively cause these very high eccentricity orbits to tend in the direction of the center of the galaxy. And it quantifies it more than that. It actually goes as far as to give an actual prediction right here, a numerical prediction rather than just a very hand-wavy, like, oh, it should be in this direction. It actually gives us a really strong prediction before it actually checks out the data. This is the same data, by the way. This plot right here, these orbits, are these orbits in purple. So here's this big one right here. That's this big one right here. And it turns out that if you throw an arrow down towards the direction of the center of the galaxy, all of these things, as they reach their aphelion, their furthest point from the sun, more or less align with that line. Therefore, modified Newtonian dynamics, as presented here, is a solution to this problem, thus not needing a Planet 9. They also do the same phase space trick here, and you can see that all of the dots, they're clustered. All of this extra phase space is completely empty. Again, another point in favor of this idea that MOND could solve this problem. But here we get to the rub. The reason that I and a lot of other astronomers can't really get behind MOND is that it's very, very hand-wavy. I mentioned before, there's this part right here. I didn't really go into any detail about it, and that's because there isn't really a lot of detail about it. If you look this stuff up, this is just some function. We don't know what it is. And a lot of times that function gets changed to meet what we want it to look like. It's not very scientific, and I'm not accusing the writers of this paper of doing that. I want to make that very clear. I am nowhere near the level these guys are. These are research astronomers. I'm not trying to badmouth them. But I am saying that modified Newtonian dynamics directly requires us to effectively throw darts at a dartboard in terms of what this function here is. And that can be scientific. When we do the search for dark matter, we do that all the time. We're like, we think a particle that could be dark matter is this, and then we go searching for it, right? It's a little backwards, not the best. There's a lot of critique in that way too. This just doesn't feel right to me though. We have a lot of evidence that shows us that there probably is extra mass there, and it's a much, in my opinion, more elegant solution to just say there's a particle that we don't know the properties of, rather than saying, you know, oh, well, we have general relativity, which describes everything so well, but then we also have to add to that. It just feels weird. And like general relativity, it predicts everything that we've seen in the universe so far very well. It'd be crazy to me that this phantom mass idea, this modified Newtonian dynamic idea, was actually what was happening. It feels weird. And that doesn't necessarily mean it's wrong. But I figured I'd give it some time in the limelight, so hopefully you found that interesting.